In this concept check question, you're asked to draw the Lewis structure of H2CO. So go ahead and pause your video and take a minute to draw that Lewis structure. Okay, we'll start by determining our total number of valence electrons. Here we have 2 from hydrogens. We have 4 from the carbon and 6 from the oxygen, giving us a total of 12 electrons. Okay, then we'll draw our atoms, and we'll put the carbon and oxygen in the middle, and we'll place the hydrogens around the edges. And you might not know where to put the hydrogens yet, so just kind of put them somewhere around the edges for now. Then we'll add the valence electrons, 1 for hydrogen, 4 for carbon, and 6 for oxygen. Then we'll make some bonds between the atoms. And this is where things can sometimes get tricky. You might not know which bonds to form, but start with the ones you do know. We know we need a bond between our central atoms, the carbon and the oxygen. And the carbon almost certainly has a hydrogen on it. And then the last hydrogen, I could imagine bonding to the oxygen or the carbon. So we'll try both. In blue, we'll bond the hydrogen to the oxygen, and we would get the Lewis structure shown in blue at the bottom. In green, we'll attach the hydrogen to the carbon instead, and we would get this Lewis structure. And in this green Lewis structure, we're left with a single electron on the carbon and another one on oxygen. So those would combine to form another bond, giving us a double bond between carbon and oxygen. And if we check our structures, we find that the green one is best because the blue structure doesn't give all of our atoms an octet. The carbon has only 6 electrons, which is unfavorable. So the green structure is our best, our correct Lewis structure. Okay, here you're asked to convert the structure below to a skeletal line drawing. And this time I won't convert it to a Lewis structure first. I'll draw the line drawing directly from the condensed structure, but if you need to draw the Lewis structure, then absolutely do so. I'll count the carbons in the main chain first, and find that I have 6 carbons. So I'll draw out a 6-carbon chain. Okay, then I'll add any groups that I have to that chain. I have an oxygen doubly bonded to the 3rd carbon, so we'll add that. And then at the 5th carbon, I have a triple bond, so we'll add that in. And then we'll take a look. This structure is almost okay, but this triple bond is sp hybridized. And we know that sp hybridized carbons have a linear geometry, but that's not what I drew. So when we draw line drawings, we need to accurately depict the geometries. So we really need to draw the triple bond in a linear fashion. Okay, so this second structure is much better. A bent triple bond makes me cringe, and it was super hard for me to even draw it here for you. Okay, the linear depiction is the correct one. This question asks you how many hydrogen atoms are present in the structure shown. So let's remember that the hydrogen atoms on carbon are the only ones not drawn in a skeletal line drawing. So we can just go through our structure and make sure each carbon has 4 bonds. If it doesn't, then we'll add a hydrogen until it does have 4 bonds. So as I go through the molecule, I'll just make sure I check all of the carbons by putting a yellow dot as I go. On the right, this terminal carbon has 1 bond drawn in, so it needs 3 hydrogen atoms filled in to make 4 bonds. The triple bonded carbons already have 4 bonds, so they don't have any hydrogens on them. This carbon has 3 bonds, so it needs 1 hydrogen atom. The alkene carbons have 3 bonds, so they each need 1 hydrogen atom. And then these carbons over here, these are called methylene carbons. They each have 2 bonds shown, so they each need 2 hydrogen atoms filled in. Then once they're all drawn in, tally them up, and we find that we have a total of 10 hydrogen atoms in this molecule.